Остановился, зажег. Звук только выключил. Да. Как-нибудь высветим уже. Хорошо. Еще? Понятно. Так, делиться. Понятно. Делимся экраном. Трансляция экрана, да? Да. Где? Начать. Остановить. Так. А теперь сейчас чуть высветим. Okay. So I would like to thank the organizers for inviting me to speak at this nice semi-bed conference. And I'm going to talk about some recent development. So this is joint activity during maybe last 2 years with Misha Berstein, who is here, and my 2 former PhD students, Pasha Gavrilenko, who is now in Geneva, and Kolya Semenyakin. So they both have unfortunately to leave, and Kolya is now in Holland and moving to Perimeter Institute. And so this is about some development of what is called cluster integrable system. It's a bit slow, yeah? When you move, it reacts very slowly. But okay, so I see. So that's about the topic we discussed here many times. Some so-called cluster or Goncharov Canyon. GK means Goncharov Canyon, the famous name integrable systems. The most well-known examples contain relativistic Toda systems and slightly less well-known the XXX like spin chains, just to be related not only with the bad part of the conference. And actually, so the conference is about integrability as usual, and everyone speaks about integrability. But here the main point is that there is a simple way why these systems are so interesting, because there is a simple way to go out of integrable situation, and just by Deuteronomization, and from them, by this simple procedure, you're getting Q difference Painlevé equations, or more generally, Q isomonodromic deformations in high rank, and the solutions to these deuteronomized, already non-integrable systems are given by partition function of supersymmetric gauge theories in 5 dimensions, so actually in 4+1 compact dimensions. So these are the examples of well, more or less physical theories, multidimensional physical theories, and the statement is similar to very well-known statement. Like the simplest example is that the partition functions of matrix models are given by tau functions of integrable systems. So here everything is more complicated. We go out of integrability, but in a controllable way. And so, well, this picture, of course, is not completed. It has many white spots, and that is why I decided to concentrate on one of particular spot of the relation with this Q Painlevé. From physical point of view, this is the SU2 gauge group, and restricted amount of multiplets less than 8. which is in 5 dimensions, a sort of analogy of asymptotically free restriction for SU2 less or equal to 4 in 4 dimensions. So, but I will skip, since we are in Mathematical Institute, I will maybe skip all this physical argumentation and try to draw simple pictures and just count, add, and extract simple numbers. But this is just the original motivation. And I wanted to say that even this picture with Painlevé was not completed by previous analysis. It had some important gaps, white spots, and in order to fill these white spots, you have to go beyond. So what is written here on top of all these statements. And there are many, well, obvious ways to go beyond, to consider, instead of SU2, the higher rank case that will give you, instead of some simple Painlevé examples, some more complicated isomonodromic deformations. To consider so other series, what is called here by other series, is that this cluster or Goncharov-Kenyan integrable system has a different representation, like an integrable system on a Poisson submanifold in in loop group of A type. While if you go to other series, so in about BCD, something is now known about other series. I would say that nothing known, at least to me. This is definitely some coming out of this Goncharov-Kenyan class. These are two options, and the third option is maybe mostly important, and I will try to concentrate on. So it's the, how we call it now, the Goncharov-Kenyan reductions. So so some reductions of these Goncharov-Kenyan systems, which we believe preserve this cluster structure. And this is definitely going out of the previous class, but so hopefully, which we're now completely sure, I would say, that at least this allows to fill totally the gap with this Painlevé correspondence, cluster Painlevé correspondence. And that would be maybe the main point. I will try to give some exact comments. And also these Goncharov-Kenyan reductions allow to study different class. So the integrable systems on modular spaces of flat connections, because there are several examples of well-known manifolds. If speaking about geometry, the manifolds which allow to introduce the cluster coordinates in different charts, the coordinates which are related by rational transformations. And this very well-known, or this Goncharov-Kenyan example is the Poisson submanifold, as I said, in Lie group. And it has relation to five-dimensional supersymmetric gauge theory. Doesn't write. And okay, that's it. So something is wrong here with the system. Let's try it once again. But if it finishes, then maybe we'll have just to put it somewhere. Yeah. And so what I wanted to say is that this another class of manifolds, the modular spaces of flat connections, so also Teichmüller spaces, which also admit these cluster structures. It's a step towards understanding of integrable system related with four-dimensional supersymmetric gauge theories. This is called the Goncharov story. Okay. Yeah, and maybe finally, I just realized when I had the previous talk of Serezha that why these two talks were unified in one session. So the organizers are very talented because as for him and for me, a very important notion will be zigzag in what follows. So, and well, to avoid any wrong associations, I would maybe what's happening? Try to rotate. It's not rotational invariant, yeah. Yes, to use it. No, but it's really it's something different, yeah. So, okay. To use in this construction. Okay. So now, what is briefly remind what is this Goncharov-Kinin system? It has many definitions, but one combinatorial or mostly geometric, so to say, is exploits its definition that one starts with a bipartite graph on a torus. On a torus means just periodic boundary conditions here and there. And one considers, so bipartite means that the vertices are colored in two colors and the edges connect on the vertices of different colors and therefore can be oriented, naturally oriented. And one considers the partition function for dimer models on these bipartite graphs on tori. So with some easy manipulation, with such partition function, one can associate a complex curve embedded in C star times C star and defined by a Newton polygon. So a curve in C star times C star with some extra data, which is defined by Newton polygon in this. Maybe I have to resign and just put a slide, Andrei, put a file on a screen because it's ridiculous here. Yes. Okay, now what to do. So, and also there is an easy way to associate a Poisson cluster variety to this. Yes, translation is stopped because I stopped the demonstration of a screen. Okay, so put it, if possible, put it just. Okay, so you have a bipartite graph, somehow oriented in an obvious way. And it defines a curve. So what is a dimer? So dimer is just you consider the set of edges of this graph, marked edges, in such a way that so neither of these two edges touch each other. So for example, this would be a dimer configuration. A good question already to the audience: how many dimer configurations can you draw on such graph on a torus? If someone answers, it would be very nice. And then you just sum up over all these dimer configurations. So the original variables are wedge variables, some functions on the edges, which can be thought of as abelian gauge fields with values in C stars. But then if you, as I said about manipulation, if you slightly normalize this, so you divide, normalize to some, single out some dimer configuration, then due to these properties, that would be just a sum over loops. So sum over dimers goes into sum over loops. And then you apply Poincaré lemma, and you just find that there are two kinds of loops going around faces and loops going around some basis in homology on T2 of T2. since this is a graph on a torus. So it's important that this homology is two-dimensional, and the dual elements of cohomology we denote by lambda and mu. These are two C-star valued numbers. And so finally, you get out of this partition function the sum of lambda A mu B FAB of x's, where x's is the set of phase variables, and lambda and mu, so the sum here are over the homology classes of the corresponding loops. And this is f of lambda and mu. So the equality, the zeros of this f, this is what is an invariant object, because as I said, the definition of f itself requires a lot of additional manipulations, but equality of f to 0 gives an equation of a complex curve, and just delta is the Newton polygon of this curve. It's just a collection of points, integer points in the plane with the coordinates a and b, just the convex of these integer points. So this is how you get an equation of a spectral curve. And what is also important is that these coefficients are actually, with some, again, additional headache, they are Poisson commuting functions on a cluster variety. And so the coordinates on this cluster variety, the cluster coordinates are these x variables. So the field strength, if you wish, of this gauge field. And the Poisson bracket is defined in a very nice geometric way. So here is the connection with what I said previously. So you see this is a graph, and it's originally drawn on a torus. But that means that we somehow fixed here the fat graph structure. So we said that these are the faces. If we now choose different choice for the faces, and namely glue the faces along the zigzag paths, and zigzag paths are the paths which turn right at vertices of one color and turn left at vertices of different color. So these are also closed curves on this graph, and if we glue the faces in such way, we obtain some different dual to torus surface, dual surface sigma, which, well, accidentally, in fact not accidentally, is similar to the complex curve sigma defined by this equation. And now the point is very simple, that generally this is, as I said, a surface of some genus G. In our case, it will also be 1, but generally it is higher. And now the old faces on torus become some non-trivial loops on this new surface. And what you take an intersection form in the first homologies of this dual surface sigma, and this intersection form defines you the Poisson quiver such that for this original phase coordinates, you get a logarithmically constant Poisson bracket. So defined by this quiver Q, xi, xj. Here, no summation. So this is what is called the cluster coordinates. And for example, for this simplest example, if you start with, then the Poisson quiver will have a very simple form. It will consist of four independent variables corresponding to 4 faces, and they will all have the Poisson bracket with the coefficient 2. And such Poisson manifold has obviously two Casimir functions. So one is the product x1, x2, x3, x4. And another is just, say, a product of these two opposite, or these two opposite, doesn't matter. So the effective dimension of phase space is 2. So now, well, what I wanted to say is that there are many ways to demonstrate integrability here. Файл нельзя засветить, да? Файл нельзя засветить. А вот который я кидал куда-то там, Маша. So there are two ways to demonstrate here integrability. The first one is again very simple and say the version of Liouville-Arnold theorem, and it looks the following. So the statement is that so as we know from physics, then if we have such an equation with a Newton polygon, and then boundary points of this Newton polygon boundary, call it by B, they correspond to the Casimir functions. And their total number is B minus 2, which gets out of B minus 3. 3 are 3 renormalizations of the coefficients in these equations, which you can, these variables you can eat by renormalization, plus 1. 1 is always this Q Casimir, which in integrable citation is always equal to unity, just because you see by its definition, so these are the phase variables, and if you take the product of all phases, this is just the loop, Wilson loop of a gauge field around all possible phases, which can be contracted to a point, and therefore it's obviously unity. And integer points of this Newton polygon, they correspond to properly normalized, being properly normalized, they correspond to non-trivial integrals of motion, which are in involution with respect to this Poisson bracket. And one simple thing is this, the application of peak formula, that twice the area of a Newton polygon is equal to B minus 2 plus 2G, where B is the number of boundary points and G is the number of integer points. And so it simply says that, so this is the total dimension of a phase space, so this is the number of phases. And if you extract the amount of Casimir functions from there, then you get twice the number of integrals of motion. And so that's why this system is integrable. And well, the most easy way to derive this formula is to just replace this by the number of phases and to apply twice the Riemann-Hurwitz formula, first for T2 and then for sigma. So V, the number of vertices and edges, is the same in both cases, but here on torus, this is the number of faces or the total number of your variables, while on a dual surface, and it is 0 because it's torus, and on a dual surface, you have the number of faces equal to the number of B, so this is the number of boundary points. This is the same as the number of boundary segments, and just boundary segments in this construction are identical to zigzags. And so this is the Euler characteristic of a dual surface. So just from these two formulas, you again get the proper counting. Okay, so this is the Goncharov-Kenyon story. And what I wanted to say now is that a part of this Liouville-Arnold integrability, you also have here some more simple mechanics of discrete integrability. So basically, it comes from the action of so-called cluster group or mapping class group of cluster variety, GQ, which is the group of automorphisms of the quiver. Generated by Poisson transformations, so-called mutations, and possibly permutations of vertices. And so yes, single mutation doesn't preserve a quiver, but a sequence of mutations supplemented by permutations can preserve a quiver. You're absolutely right. So each mutation is a Poisson transformation, but you go to some other chart. What can happen finally? This is a very good example of this quiver. So if you take a mutation at each of these points, you, as you know, reverse the arrows here, and you have to add 4 arrows more. But then if you make a mutation, another mutation in an opposite point, you come back up to permutation of the vertices. And what you get is that the quiver remains to be the same, but the variables, say the cluster coordinates here from here, they transform actually to some other variables, which are the rational functions of the previous ones. And the statement about integrability means that h of x remains to be invariant. And actually, this is true if you properly normalize the integrals of motion. It is true about the whole action of this mapping class group. So this is a quite non-trivial statement, which somehow may be related with the fact that these Hamiltonians are cluster functions, so that these are some Laurent polynomials in cluster variables, possibly of fractional powers. Because when you make these birational transformations, I had formulas on my transparencies, but they're somewhere lost in the file. So generic functions acquire poles in a different points, but these functions remain to be Laurent polynomials, and they actually remain to be, so they're invariant under such transformations at, which is very important, and at q equals to 1. Now, Deuteronomization is a very simple statement that many properties, for example, the symmetry group, remains to be the same if you just violate this condition. If you say that q is some number, so it is at any value, it remains to be a Casimir function of Poisson algebra, but it is no longer unity. And the point of Deuteronomization is that under such procedure, instead of an integrable system, you get its non-autonomous analog, and namely isomonodromic deformation. And for example, remaining this condition here, from the invariance of this system, you get the Q Painlevé 3 equation, which is a non-autonomous 5-dimensional version of a Sine-Gordon system. So this is the statement about the autonomization, and at some moment I still want to show the picture. Do you have my file anywhere? Where can I send it to you? Do you know? Again? but we have no time for my starting. It suggests to send a report about the problem. В чате он есть у Маши. Because also at certain moment it gives me так, ну я могу, понимаете, если бы я мог, я бы послал как вам, так и не вам. И вам, и Андрею, кому хотите. В чат какого зума? Вот. Ага, хорошая идея. No, it's the problem is that it kicks me out of the Zoom conference. That's the point. Let me try. Okay, Mish, since I have your I sent you, Mish, and you maybe can transfer it to Andrei. Okay, so now what I wanted to say that so this all works, as I said, so torus is fixed because you have to get an equation of a complex curve, but the genus of dual surface can be arbitrary. The Painlevé systems are distinguished by the fact that for them, so first fact that for them G equals to 1, and there is a sort of duality between T2 and dual surface, sigma of genus 1. In certain sense, the role of dual cluster coordinates on in this dual system is played by spectral parameters with a symplectic form. One can say very roughly that they have some symplectic form or Poisson bracket given by this formula. And then you can do another procedure like we did on this right blackboard for cluster variety itself. We can take a dual surface, consider its faces, the zigzag paths, and consider now an intersection form of these zigzag paths given simply by intersection form in first homologies of a torus. And such procedure defines you a dual quiver, which I denote by quiver Q zeta, zigzag quiver Q zeta. And it's simply, so it can be read off the Newton polygon. You just associate the vertices of this quiver with the boundary segments of the Newton polygon, and the number of arrows between them is just given by this intersection form. Or what is it? This is just a vector product of any two boundary segments of this Newton polygon. And the point is that in such way we construct this Q delta, and this is a Newton polygon for this my Toda system. And you can easily see that the dual quiver will be the same. So for Painlevé system, one can roughly write so that this duality between torus and the dual surface extends to the duality between Poisson quiver and zigzag quiver. Of course, this statement needs to be somehow explained because what can you actually say? Everything depends on particular choice of coordinates, of particular choice of a basis, but at least one can argue that these quivers are in the same mutation class. So generally, instead of a quiver itself, so it's a percent bracket in a particular given chart. But in order to study the whole cluster variety, you have to look for the whole mutation class of a given quiver. So in order to do this, one have to study the mutation class, for example, of these zigzag quivers. And once you started to do this, you find that, of course, under mutations of zigzag quiver, and this is the same as some rational transformation of lambda mu parameters, which is called, well, at least among us, the Gayota transformations. These Newton polygons transform, and not each representative of this mutation class corresponds to a curve of genus 1. You can easily get a curve of higher genus, but of a particular form with fixed coefficients, so not in a general position. And minus 5 minutes. Oh, okay, my minus 5 minutes have passed. Okay, so есть пульт у вас? Чем это листать? I will show now a few pictures, and then fortunately to all of you disappear. So, no? Вот, Andrei, можно эту фигню убрать тогда оттуда? Okay, so this is what I tried to. So if Andrei Konstantinovich gives me, no, that doesn't work the opposite direction, yeah? Minus 2 minutes more. What's the hell is? Не хочет? Ну так долистайте, давайте долистайте, я тогда покажу куда. О, это вы, ну листайте. So this is a mutation. I will make a comments. The nice comments was the words pronounced by Sergei Fomin exactly in this audience, that those who know, they know, those who don't know would never learn. So how it looks like. So please more. So this is the fact that it's Poisson transformation. I want a picture of Painlevé polygons and quivers. Sure. So this is what Serge Landau asked, and the way how you get the autonomization. Please more. So this is again more. Oh, okay. So these are the Painlevé Newton polygons. So namely, these are all Newton polygons with a single internal points and as many boundary segments as you can draw. So you see that what we discussed is the minimal one, but there is a maximal one. So this is the polygon with the number 8. So also you see that there are usually several polygons with the same number of boundary segments, and some of them are related by these Gayota transform or quiver mutations, as I said. And so this is 8. That corresponds to the case of Painlevé 6, which the last one, which has the reasonable four-dimensional reduction, and then there is once more and nothing else. But as I said, переверните, пожалуйста. So as I said, so these are the quivers corresponding to these polygons. You see that they are less than on the previous pictures. Please, one more. Yeah, and so this is the set of Painlevé systems in Sakai classification, which, if you take the denominators, it coincides with a set of symmetries presented in Zyberg's paper about five-dimensional gauge theories. So this E5, which is actually D5, is the last one, Painlevé 6. So this is E6 corresponding to this big triangle, and there are two more. And so finally, листайте, Andrei, листайте. So just to, this is demonstration of some mutations. Yeah, so this is how this extra higher genus curve of a special position. So the white points corresponds that you have to fix somehow the internal coefficients. Листайте. Okay, yeah. So these are last two cases. So theorem partially theorem, partially conjecture, that in order to get two last Painlevé equations which complete the picture, you have to consider the cluster reduction of a corresponding higher rank systems. And so here I presented two Newton polygons, which you have to consider. One more, yeah. So this is some counting, how the reduction acts on the numbers, and this is the result, yeah, to give excuses to mathematicians. So this is an exact formula for the Hamiltonian of Painlevé E7, which arises from this reduction. And the fact that Q, which was the product of all variables, now transforms to the product of 10 variables, but with some powers, shows that this is definitely a non-Goncharov-Kinin case. So I have to finish, and thank you for attention, and apologies for this belief in your technique.
Questions? Marks?
Yeah, maybe Misha has some remarks. Yeah, actually, also I wanted maybe last remark to say that when we go to study this for Goncharov situation, then the hypothesis is that there arise some interesting reductions of the spin chains, but that is still not clear.
Thank you very much. Okay. Now, lunch.
Question? I have a question.
Question?
Yeah, Andrei, I have a question. So you consider the automorphism of quiver just after you take sequence of mutation and then consider automorphism of the quiver, but there are different notions. One, you can look for what is called a reddening sequence. So then you consider principal extension, and then you just have such automorphism. And another is just as you define it. For example, in the case which you consider, which is with this 2, 2, 2, then it is. Can you hear?
Yeah, I hear.
Okay. So therefore, in this example, so there is no reddening sequence. And in another example which you give, for example, then only just arrow of length 1, just 1, 1, 1. So there is a reddening sequence. In another example which you get, there is so sometimes in your presentation there is.
Gleb, maybe I confused you because at a certain moment, due to the lack of time, I changed notation. And if you refer to the quivers with a single arrow, then it's misleading notation. For example, if I understand you, of course, correctly, for example, this picture.
Yeah. So this definition of this invariant.
4, 1.
Yeah.
4, 1.
Yeah.
Means that this is a group of 4 vertices.
Yeah.
So actually, this is altogether 10 variables.
So it is just
fragment. So it's not just a single variable with a single arrow which can be just cut by mutation.
Okay. But nevertheless, so the question. So in this automorphism, there are two differences. So one is just as you define it, and another which is obtained through the reddening sequence. And so is any difference would be because from reddening sequence we have more information about this automorphism, so it's just in some sense more interesting object.
I do not understand quite what you mean by this sequence.
Okay, so it is.
What is that?
So you have just to consider principal extension. So just
so Misha says that there are no such symmetries for our quivers, and I simply don't know what it means. But here, well, the statement is that you take more or less all possible symmetries which you can generate, and then it's some symmetry group, some discrete symmetry group, which has a lattice inside. This is its abelian part, and also some permutations, etc., which usually generate some wild group of affine system. And this this while group of affine system is a subgroup of this group of cluster automorphisms. But I'm very sorry, but well, being uneducated, I probably don't know what you mean.
Okay, so maybe.
But you can ask, yeah, you can ask
Yes.
my colleagues.
Yeah, so then we meet. I just ask you first.
Okay.
And I
Okay.
will just look. So you have this paper in archive? Or it's
It's a good question. It's also
Yeah.
better to address it to my younger colleagues.
okay. But slides are available. Okay.
Slides, I think, will be available. Yeah. Yes. Yes.
Okay. So thank you for nice talk.
And the article, I hope, will be printed. The article, I hope, will be printed in theoretical and mathematical physics. Your article. This. No? Okay. Thank you very much again. So, okay, so downstairs.